In this video, we're going to be looking at some Cepheid variable stars and discovering what they are and how they led to an important piece of work which still underpins most of what we know about the universe today, the magnitude versus period law. We can then use that with a formula for calculating the absolute magnitude to get some insight into the work of Edwin Hubble and Hubble's law. And so we'll lead up to Hubble's law in this video, but we won't look at all of the consequences of Hubble's law. So let's start with a star in the center of this image, which is Delta Cepheid. Delta Cepheid here is an interesting star. It's about 980 light years from Earth. It's a supergiant, and it's called a supergiant because it's big. It's about 40 times the size of our star, the Sun. But the interesting thing about Delta Cepheid is that its brightness changes over time, and over a reasonable length of time, so over a few days, you can actually observe the changes in Delta Cepheid's brightness. And I'm going to show you some data on that now. So here is the data for Delta Cepheid taken over just over a week, and you can see in the table here we've got in our first column the time of observation measured in days from 1 to 10, and there's a 2.1 in there. That must have been two measurements taken within the same day, and again down here 7 and 7.5, so there's actually more than 10 measurements there. And then over here, this is the brightness that was observed in the telescope measured on the astronomer's apparent magnitude scale. And remember that this scale is a little bit odd because it's logarithmic if you compare it to the intensity of the star. And it also has the oddity that the brighter the value, the smaller it is. So a value of 3.6 here is actually brighter than 4.4. Okay, the bigger the value, the dimmer the star. So what you can do now is go away and plot this data using a spreadsheet, and then come back and we'll discuss your results. So here I've drawn a graph of apparent magnitude on the y-axis, the observation time on the x-axis. And you'll note that this graph is backwards with regard to brightness because 3.6 is brighter than 4.6, which is dimmer. In fact, the change from 3.6 to 4.6 is a change in brightness of a factor of 2.5. So as we go up the graph, we're getting 2.5 times dimmer from 3.6 to 4.6 because there's a whole magnitude change. Now you'll notice that Delta Cepheid is getting brighter and dimmer and brighter. And one of the things that we can do, and this was the work done by Henrietta Leavitt in about 1908, she had measured the period of these stars' variation of brightness. So we could do the same thing. We could measure from, for instance, over here to over here, and we could measure in days the variation of a whole period's worth of brightness. And that comes out at about somewhere between 5.4 and 5.5. The other thing that we can measure on this graph is roughly the average brightness of the star during this time. Okay, so if we did that, we could say that the average brightness is somewhere along this midline. So I guess that the average brightness is roughly around 4, which is what we're going to use today for our variation of brightness. So we've got these two measurements from the graph. We've got the period and we've got the average apparent magnitude. Now what Henrietta Leavitt did was she did this for lots of different stars. And when she did that, for stars that were all in the same region of the sky, in the Magellanic Clouds, she realized that there was a pattern. Okay, on this next slide, we have got some data for several Cepheid variable stars. We've got 3 stars here, and you'll notice that they have different periods, 3, 10, and 30 days, and they have different brightnesses. And the interesting thing about these brightnesses is that as the period gets larger, so the star gets brighter. Remember, a smaller magnitude value means a brighter star. Now these magnitudes are absolute magnitudes, not apparent magnitudes, so we have corrected in this data set for the distance between the Earth and where the star is. And we'll do that process for Delta Cepheid a bit later in this video. So here I've plotted that data using a spreadsheet and put the magnitude, remember it's an absolute magnitude, the mean value of it on the y-axis, and I've put the period of variation for our stars on the x-axis. And it looks like there is a relationship there, but it's only really when you plot it on a logarithmic axis, like the one over here, that you actually can see that it is truly logarithmic. Here I've got a logarithmic axis for my period. 1, 10 and 100 occupying the same amount of space is clearly logarithmic, and my magnitude scale is already logarithmic. But what I've done here is I've reversed it so that as we go up here, the value gets smaller and therefore we get brighter. And you can see that the relationship is now clearly logarithmic, because as my period increases logarithmically, my intensity increases logarithmically. Remember, magnitude scale is logarithmic. So the only thing we've got to do now is to make sure that we can plot Delta Cepheid and see where it fits on this data set. Remember that this work was being done back in the 1900s. In fact, Henrietta Leavitt didn't have the distance data, so she wasn't working with absolute magnitudes, but she was taking objects in the Large Magellanic Clouds, and therefore she pretty much knew that the objects that she was looking at were all in the same place. And if they're all in the same place, then you don't really need to correct the apparent magnitudes for absolute magnitudes. So she didn't need to go through that step, but in many A-level specifications we do. So we're going to go through that step now for Delta Cepheid. So here we go. From our first graph, we know that our apparent magnitude, little m, in our formula, was about 4. And we know from looking up data about Delta Cepheid that it's 272 parsecs away. So what we can do is we can now use this formula to correct for the distance between the Earth and Delta Cepheid and allow us to find the absolute magnitude, capital M. Now this formula works in parsecs, and you can see here that the value d that we're going to be putting into our formula, 272 parsecs, is measured in parsecs, and so is the value underneath it. This is 10 parsecs, and this is the reference distance for all absolute magnitudes. Astronomers had to pick a distance from a star to measure the absolute magnitude, and they picked a nice round number of 10 parsecs. Since they were measuring the distance to stars in parsecs anyway, they thought that this was a good distance to measure the magnitude absolutely of a star. So here we go. Let's now put the numbers into the formula and rearrange, and we get a value of minus 3.17. Okay, so minus 3.17 is smaller, 7 magnitudes smaller than the apparent magnitude. Why is that? Well, if you move from 272 parsecs away from the star to just 10 parsecs away, then what you find is your star looks a lot brighter, and minus 3.17 as a magnitude is much brighter than 4. So we can now take the information from our first graph, which told us that Delta Cepheid had a period of between 5.4 and 5.5 for its variation of brightness, and we can plot the minus 3.17 absolute magnitude on our graph, and there it is. And you might be wondering why it's not sitting right on the line, especially since Delta Cepheid is given as one of the prototype stars for this kind of work? Well, quite simply, astronomy is complicated and astronomy measurements are messy, and it turns out that there is in fact a dust cloud which reduces the magnitude of the star that we observe from the planet. If we take account of that dust cloud on the variation in brightness that it causes, then we can actually move our delta Cepheid up in brightness. Up means getting a lower value onto the line, and there it is. The important thing about this work is that Henrietta Leavitt discovered in 1908 that if you measure the period of the variation of a Cepheid variable star, you can use this law, this line, this linear relationship to work out how bright that star is. And that's an amazing piece of work, because that means that if you know how bright a star is, you can actually work out how far away it is using the inverse square law. We know that as the light from a star spreads out in the universe, as it travels away from that star, the intensity of the star gets less, and it gets less on a very predictable law, the inverse square law. So if you know how bright the star was originally, you can work out how far away it is by simply applying that piece of information and how bright it looks from the planet Earth. Amazing stuff. This work led ultimately to Hubble's law, and in fact it still underpins many of the measurements that we take of the universe today. So Henrietta Leavitt, who discovered this law, is a bit of an unsung hero in astronomy, or at least she was. Nowadays we've realised that the contribution that many women make to science domains is much larger than had been previously recorded, and this is one really good example of a woman whose work is now sung widely amongst educators so that everybody knows what she did and how important her work was in determining what we know about the universe today. So in about 1924, Edwin Hubble was working on measuring the distance that stars were, or sometimes galaxies were, from us versus how fast they appear to be moving either towards us or away from us. Away from us is the recession velocity. So he used Henrietta Leavitt's work, which allowed him to figure out the brightness of a star from its variation in its brightness, to then compare that against the brightness that it looked from the planet Earth, and hence work out the distance. And that's a little bit like doing a backwards version of what we did in the previous slide. So you'd use Henrietta Leavitt's law to work out the absolute magnitude. Then you observe the magnitude of the star from the planet Earth, and then you use this formula to get the distance in parsecs. You've then got the data you need to plot the distance axis of Hubble's law. If you then use the redshift to work out the recession velocity, you can now see that Hubble had all of the tools in place. In effect, he was standing on the shoulders of the giants in physics, like Henrietta Leavitt, that came before him, to come up with the discovery of the Hubble's law, which shows that there is a linear relationship between the distance that a star is from us and how fast it is moving away from us. And that underpins virtually all of our modern ideas about an expanding universe, about the shape of our universe, about the geometry of our universe, and even about the idea that our universe may well have had a beginning called a Big Bang. So Henrietta Leavitt is in effect providing the law that allows us to discover the Big Bang, and that's why she was so important. Hope you enjoyed this video.